Can't say what graphs are. So I start recording. So guys, we were interested in like the graph search. Okay, not like building graphs or the structure of graph, but we will look at how we can make a graph search. We can call this explore a graph, and like these are topics. Like what we mean by the explore a graph. We mean find the path from node S to node P, or find all paths from node S, find all nodes reachable from S, find all the nodes in the graph, find all the edges in the graph. These are the topics, these are the questions that we are interested in. Like I'm not gonna, for example, give a structure and ask if this is a graph or not. You know, this is not data structure class. This is like algorithms class. We interested in these problems and solution of these problems and how we can look at these problems in algorithmic way. But I will have some kind of like to recall to make sure that like we're on the same page. And a graph G can be shown as a V and E, where V is set of vertices and E is set of edges. So each like vertices are between the vertices are connected with the edge, right? So there are two vertices and they're connected with the edge. So E can be shown as a U and W. U and W are the vertices. Okay, guys, and the graph can be unordered. I'm sorry, like this U and V can be provided as unordered, which means the graph is undirected. And there can be ordered, like the UV, UW is different than WU, which means that this is directed. Okay, guys, so there's a graph, an example graph, and here we are seeing that the A, C, B, and D, A, B, C, D, and these are the graph, like this is undirected, which means that we can go from A, we can go to D from A, like we can go to B, C, and D from A, right? And also it's vice versa. We can use the same path and in reverse order. So we can go to A from C. Okay, guys. And also here's the same thing. This is like this is the directed graph. So we cannot go to B from A, right? Because this arrows shows the direction, and it says that we can only go to A from B, not the vice versa. We can't go to B from A. And this is also like the two-way. It can be like two edges to show that it's a two-way connection. Okay, guys. So if you would like to go to the C from A, right? We can go this path directly from A to C, or we can go to D first, then we can go to D from D and D to D to C. This is how we traverse the graph, and we look at like how should we traverse the graph to find what we want. So why the graphs are important? And this is our motivation, and because like they are used in web crawling, right? Web crawling means that like when the Google make it like this searching, right? They do this like the graph structure to traverse the entire web, because the webs, like the pages, are connected to each other with the links, and by traversing these links we visit the new pages. So this is like how they crawl the web and generate this entire search structure for us, the search engine. Also, social networking is another like another feature, another problem that we use graphs in. And here, like in the figure, you are seeing that all these people are connected to it, social networking, like branding or following. And we have some kind of problem, like say that friends just bring all of your friends, or there'll be some kind of thing that called the friends of friends, right? For example, from this person, if you want to call this person friends of friends, right? Or you can have friends of friends of friends, like three distance for people. We can do something like that. And network broadcasting, another application of the graphs, and like this is the same thing with this shorted path. You know, like the networks that are routers are connecting to each other. And if you would like to broadcast something, like which path you need to follow to make like the shortest path you need to find. So we use the graph to symbolize the network structures. Also, garbage collection, another structure, another problem that we solve with the graphs. Like the garbage collection, like in the modern world, in the modern operating system, basically free they free the object or instance. They are not reachable anymore. So when you write a program, you create an object, you create variables, and after some time, like you free the object from from your program, but you don't need to free the object from the memory. But the operating system checks that if any instance is not reachable from your program or another running program, then simply they just assume it's garbage and they just read for you, so you can have the free memory space for these new variables or new instances. The model checking, another problem. Basically, model checking is a formal method, guys. So it is a different field in the computer science. Basic model checking shows you that like the properties of your program. So with the model checking, you look at the entire program state path, entire program state space with a graph. You generate a graph, your entire program state space, and then you look at which state supports or satisfy your properties. And also solving puzzles and games, and like in the MIT website they talk about this Rubik's Cube problem, and we will do the same thing. Like if there is some kind of like the combination or variation in your puzzles or games, it can be matched with a graph, and we will see how we do it. Okay, guys. So here example, there's like the 2 times 2 times 2 Rubik's cubes, 2-dimensional Rubik's cubes. So we can generate a configuration graph of these Rubik's cubes. For each state, we can have a node in our graph by naming the move. For example, like rotating this first thing with just on the clockwise or counterclockwise, we can name all of these, and we can have the transitions edges basically and the nodes each state. So we can generate the configuration graph, like all possible state of this Rubik's cube can be like mapped to a graph, right? And then if you like to solve this Rubik's cube, right, we need to find do I have it? Yeah, here it is. So here it is in an image. Let's say we have this whole state. Okay, this is like this initial state. The state is solved. So for each possible moves, we generate actually a state, right? If I rotate this first part on the counterclockwise or like clockwise, so I generate a new state, like also like the 3-dimensional moves here. I assume that you all know what Rubik's cube are, right? Is there anyone who never heard about Rubik's cubes? I don't think so, right? You all heard what Rubik's cubes are. So basically, guys, for each move, right, for each move we can just make from solved state, we generate a new state, right, guys? For each distinct move, we generate a distinct state. From each distinct state, we generate a new move, right, guys? So it goes like this. Like there are the set of the state of these Rubik's cubes. Like it's not infinite, right? There's some number of these states for the Rubik's cubes. It says like this is 8 factorials times 3 to 8. It's a very big number. Like it's like more than 200 million. So there are 200 million states for just these 2 times 2 times 2 Rubik's cubes. So in this R graph, we would have like these numbers of the program state for solution of these Rubik's cubes. So how we can solve the Rubik's cube by using graph? So each state of these Rubik's cubes is matched one of these states, right? And then we can just go backward. Assume that the state of our Rubik's cubes is here. This node represents the state of these Rubik's cubes. And then we just need to go back, right? Just undo the move that creates this state of this Rubik's cube here. And the final state is the solved state, right? We cannot go from there. So this is how we can solve this problem, solve the Rubik's cubes. And actually, there's like the number of states, like the farther away, right? The farther away, there's also the number of there's a limit to create the number of moves for a node. So this is called the diameter of the graph. Like here for this Rubik cube, it's going to be 11. So which means that we can generate a new graph, new node. I'm sorry, we can generate a new node in 11 move. But if you do another like 12 move, this 12 moves generate the cube state that's already here. So your 11th move basically goes backward, which means that any state of these Rubik cubes can be solved in 11 moves. Okay, guys. I want to say this thing again, like diameter means that the size, not the size, but the level, like something like the same with the tree. Like you have the depth or height of the tree. So it is the same with the graph. This is called diameter, which means that the farther the two nodes, the farther away, and number of the moves that you need to go from one state to another state. Not another, but the farther away state. Okay, guys, this is 11 for this problem. If you do the 12th move from this state, you go backwards. You cannot go from further. Okay, guys. So I'm explaining this because I'm gonna give you a question about this Rubik cube in like one of your problem set. I want you to solve this problem. So how we can represent this graph? So there are, like I said, there are 200 million states. So how we can represent this graph? We can use the adjacency list, which is a fun way, nice way to represent a graph. Like we use a hash table. And our hash table called adjacency A, D, and J. And no problem. And for each vertex, okay, guys, for each node or vertex, we're going to have linked list that store the adjacency of these V's neighbor. So, for example, for this graph, we have the A, right, as a vertex. So we have the A, and A adjacency list of the A is B and C and D, right? Because A is adjacency of these three vertices. And here, the node, the vertices V is your key, right? Because and it can take a key, and this key, the value is the linked list for this key. Okay, when you provide this V, the vertex V, to your hash table, you will receive a linked list which stores V's neighbors. So for the A, let me, if I can type it. So for the A, right, A, if I can adjacency A, I'll return a linked list, which is B, right, C, and D, for example, the linked list. So adjacency B is going to be equal to only A. Adjacency C is going to be A and D. So it doesn't matter the order here, right, guys? It doesn't matter the order, like it's just linked list. I just type them like in like alphabetical order, but it doesn't matter for us for unordered list. And then for D, we have A and C. So when we look at this adjacency list, actually we can just recreate this graph. Okay, guys, like let's start with the A. We can put the A first, and we say, okay, there are three nodes. They are connected. They are neighbors of A, and then we can just create this A, B, C, then D, right? But just having these vertices. And with the final, like with the from C and D, we can just use this one again as well. So we can create an entire graph by just looking at this adjacency list. Okay, guys. So this is not like the complexity of the graph, but this is how much memory we're gonna use, right? And what is the answer for this thing? Number of the vertices plus number of the edges, actually times 2. Because like for example C, for example, C is included the adjacency list of the A, but at the same time A is included the adjacency of the list of the C. So which makes it like we're gonna use, like we're gonna store one vertices for we're gonna store one edges twice for each neighbor, right? Because this is unordered. If this will be ordered, right, guys? then we're gonna have, let's say we're gonna have only one way to store it, then it's gonna be like the just number of the vertices plus number of the edges. So this is like how we can represent a graph with the edges in the list. And second, we can do this object-oriented fashion. It is simple like v.neighbors. So when we create a node, we can just say v.neighbors as a adjacency.v. It's gonna be actually the same, but they're gonna be like the object-oriented fashion. Like when we just vertices, vertex A is equal to, let's say, new vertex in object-oriented fashion. Right, guys? Assume that all of the other vertices are there, and we can do A dot neighbor, right, guys, equal to new linked list. And let's say we have B, C, and D. Right, guys, this is how we can create the graph in object-oriented fashion, right? Assume that B, C, and D already created as vertices, right? So this is how we can represent the graph. For each node, we can generate neighbors, again, as like the linked list. We can do something like that. We can define something like this function. And the other way is the implicit representation, where we do not explicitly say that like what is neighbors of the graph. And here, adjacency of the vertex is a function. So when you call the function, you calculate neighbors. Okay, guys. So this is like not like this. So we not define all of these state all of the graphs here, but this is like explicit representation, right? We just said that this is like their neighbors. So neighbors of A is C, neighbor B is neighbors of A, B is neighbors of A. We have to say explicitly. But here, with implicit representation, we do not say that this D is neighbors of A. But when we call what are the neighbors of A, we calculate that D is neighbor of A. Is it clear? The difference is clear. And this representation is useful when the graph is too big to store. Okay, guys, because assume that for the Rubik cube, we have millions of states, right? Store all of them with the edges and the vertices. It takes like so much memory. But if we define a function that calculates the neighbors, right? If we give the A and let me calculate all of the neighbors, we can do it. And it's gonna be like much more not easier, but much convenient in some cases, such as if the graph is too big. For example, Rubik cubes. So any question about this stuff so far? How we can represent the graphs and what are the graphs, what is the edges, what are the vertices? If you have a question, I can answer. I would like to repeat this thing again, the implicit representation. So difference this different between this representation with the others. When we provide these representations, we already say that, explicitly say that, okay, let's say the C is neighbors of A. We say that explicitly. But here, with this representation, implicit representation, we do not say this thing explicitly. But we define a function. Okay, guys, we define a function about the neighborhood. And if we provide a neighborhood, we ask for the neighbors of A, this function calculates the neighbors of A. Okay, guys, and this is useful when the graph is too big to store. Okay, guys, and when we also, if this graph is too big, then most of the time we just need a part of it, a small part of the graph as our answer. And therefore, we don't need to store all of these graphs and then make a search. But basically, we can calculate what are the neighbors, or what is the part of it that we want. And Rubik uses an example for it. So for example, we are on this state, let's say, we are on this state, initial state, and let's say, I would like to bring the, let's say, like you do one and let's say you do another move. And after this point, you just want to see what are the next move, what can be the next move. Okay, guys, like their number of the moves are limited, right? From this in a state, number of the moves is limited. You cannot make the infinite moves from one state. I don't know how can you make that. Maybe 1, 2, 3, 4. There are 4 pieces, right? 4 big pieces. So this is 1. This top half is 2nd. This bottom half is 3rd, and this second side, right? So what I mean is, so this is the first side that I can move, right? Clockwise or counterclockwise. This is the first, second 2 moves. Or there's also like the back side, this side, right? I can move this side, like again, counterwise and counterclockwise. 2 moves here, it's 4. Also, if I just split from the top, right, from the middle, so I can rotate this thing like this way or this way. There are 2 moves here and 2 moves here, 8 moves. So from each state, we have only 8 moves. Okay, guys. And if we would like to say that, okay, from one state, I would like to see what are the possible moves, right? I just need to do calculation, the 8 moves, and I can just bring the answer. For this thing, I just need to make the 8 calculations. But here, if I would like to have entire graph, then I need to store like more than 200 million states, and then I need to make a search and then grab the neighbors of the state. But this is like much more easier, right? These 8 moves are much more easier than that. It's clear, guys? And we can use explicit thing, explicit representation. Okay. So now we look at like how we can traverse this graph. We can use the graph first search, or it can call like level order. Please ignore these words, okay? Just ignore these words. Exploit state, this is exploit for. Just ignore. So this is one of my papers, so I just grab the image from here and I cannot remove this stuff. So in the level order, guys, in the level order search, we explore all vertices reachable from a node. And to do that, we go like level by level. So from if you are in this state, let me use different color. Okay. If I'm on this state, okay, guys, and if I would like to explore all vertices, I would like to see all the vertices that I can visit from this state. What I need to do is simply visit all of these edges, right? All of these edges grabs me new state. In the level order search, the thing that I need to do, I finish all of these edges by first, like the first level neighbors. And then I call this thing as a frontier. Okay, guys. It's called frontier. From here, I visit the second level of my neighbors. For each node, okay, guys, I just visit all of these nodes, possible nodes. And I call this thing as a frontier, second frontier. This collects the second level. So after some point, we're going to have the level k and level k minus 1 is called forever for this example. But there might be some end graph, right? End node, like as here. Here, this is like our final node, which means that we cannot make any more new transition that just generate a new state. In graph, they are limited, so therefore there must be some nodes, right? Which is the final node that we cannot do any more transition. So this is how we traverse the tree. Okay, guys, this is called level order. So you just traverse the graph as level by level. So you don't jump from here, okay, guys? You don't do that. But you first visit all of the edges, all of the vertices. This is like the closed one edge connected to your initial state with one edge. initial vertices, and then you do second one. From all of these, you visit again only the second level neighbors by using the edges between your level 1 and level 2 nodes. Okay, guys. So there's a challenge actually, where if this is a directed graph, maybe there's something like this. You visit this graph, you visit this node, and from this node you can go this node, and then you can go back. But this thing can be like generate a new state here. So this is make useful right now. So these two states are the same, but I can just go into the infinite loop here, right? If I not be careful, I just go from infinite loops here. And I go this node, this vertices, and go back. And this way, right? I can go till forever if I don't be careful. This is one of the challenges of this breadth-first search. And so what is the complexity of it? It is V times E. V plus E. And here V is number of the vertices and E is number of the edges. That is possible to our graph, right? Because from these vertices, we can visit all of these vertices, assumingly. And then we need to visit all of the vertices once and all of the edges just one, right? Just going one will be enough. So this is the complexity of breadth-first search, and this is the algorithm here. So you can just, this is how we can just write the Python code for this algorithm, breadth-first search. And here's the example. Because we try to explore all possible, we want to see all vertices that are reachable from S. So our S is going to be level 0 here. This is level 0. And what are the neighbors? Immediate neighbors, A and X, right? So this creates a level 1 frontier. Because level 0 frontier is just S. We started from here. And then by taking only one edges, what vertices we can visit? A and X. So this creates a frontier 1. And then for each element in this frontier, we also visit the other nodes. From the A, we just discover Z is here. And from X, we discover D and C. So this thing creates a second level frontier, right? The entire thing creates a frontier 2, which is Z, D, and C. And then from this level 2, frontier 2, we also let's go to our neighbors and we find that F and V are here. So frontier 2 is F and V. Okay, guys. But here is one more thing, right? If we are on the frontier 2, for example, we are on the D, we can also go to C, right? By taking this path. So by taking this path, we can also say that the C is the frontier 3. It's not actually correct, right? Because we already take this, we already include the C in our level 2. So this is what we need to care for. But there might be a longer path to return to state, and we do not like this. So we go from 1, 2, and 3. So we can visit 3 nodes to reach the C from S, right? But this is not the shortest path. The shortest path is actually from S to X and X to C. So when we make this traversing, the exploring new state, we need to be careful that if the state is already explored or not. Okay, guys, so this is how we can create a level 3 frontier, and all of these graphs all of the nodes are explored for the node S. So this is how the BFS work. Any question about this? I will show you another example. This is the same example that I have. So this graph is again each node is connected. So here, this is our frontier 0, is just the initial state, initial node, or initial vertex. And from here, we discover all of these level 1 vertices, and we create the frontier 1, and then we create the second level, frontier 2, and all of these vertices are needs to be if we need to visit these vertices from our initial vertex, we need to visit at least 2 edges, right? So we can keep going until like all of these graphs are explored. For here, we have the frontier R for the level R. For this set, we're gonna have the level K. For this, we have the level K plus 1. Okay, again, ignore this like the exploit state or the vulnerable state. Okay, guys, just ignore this part. So, any question about this thing before starting the shortest path problem? Okay. So to solve the shortest path problem, guys, we also need to mark the node as like these parents. Okay, we just define the parenthood of a vertex to solve this shortest path problem. Okay, assume that we want to go from S to, okay. We would like to go from the shortest path from S to V. Okay, guys. So we can go to like X, D, C, X, D, F, and V. So it's gonna be path. So there's like number of the paths are like unlimited because there's a like loop actually. Okay, guys. And we need to find the shortest path to reach the vertex V from the vertex S. So to do that, when we traverse the tree as the breadth first search, okay, guys, we mark the node's parent. For example, the parent of B, we say U, and then parent of parent, it's gonna be something else, and parent of until we find the S. Okay, guys, from this way, from the vertex U, we can reach the S, and if we go to backwards, we can reach the S to V. Okay, guys, for example, here, the parent of B, the vertex B. Yes, I do not know what is the lazy or eagle algorithms, but we'll talk about it right now. Not like right now. We can talk about it later. Okay. Yes, call grid, yeah, but we will talk about them later. So here, when we are on the, let's say we have V, when we make the breadth first search, okay, guys, when we find the X and A as a neighborhood of S, we mark S as the parent of X and parent of A. Okay, guys. So S become parents of A and X because like we discovered these vertices when we are on the S, vertex S. And the second level, for example, when we discover Z, right, from the A, vertex A, then we make this A as a parent of vertex Z. Okay, so here, when we look at so it's going to be same thing here. So vertex D and C, so X is the parent of the D and C. And here we said like we can make 2 parents for F, right? We can make it C or we can make the D. It doesn't matter which one you go first. And if you start with the C, then the parent of F gonna be C. If you start from the D, the parents of F gonna be the D. It doesn't matter. And finally, so if you like to find the shortest path from S to V, we all need to just go to parent, right? So V, if you need to see the next node, we just need to look at the parent of V. And the parent of V is equal to C, and parent of C is equal to X, and the parent of X is equal to S. So this is the shortest path, basically. So by using the Bradford search, we also find the shortest path problem. If you like to go to vertex C to vertex S to vertex V, we can solve this problem by doing Bradford search and marking all of the nodes as a parent. Marking the vertex that we parent of the vertex that we find from here. Any question about this thing, guys? How we solve this shortest path problem with the BFS? So what is the complexity of the shortest path problem, it's number of the adjacency vector, right? Number of the vertices of adjacency vectors, so all the vectors, all the vertices, right? Because this is how much we need to visit to create this thing. I'm sure this is not the short, but this is for like the BFS. Okay, guys, the complexity of the BFS is equal to the size, not to the summation of the size of the adjacency list of each vertex, right? Because even if we are, let's say we are on the D, right, and we would like to discover the frontier tree, we need to make this transition and see if this vertex C is already included or not. Therefore, it's also the same thing, right? If we are on the C and we would like to discover the frontier tree, to say that D is not included in frontier tree, we need to make this transition and see if D is already explored or not, discovered or not. Okay, guys. Therefore, the complexity of it is the total number of the vertices include inside of the adjacency lists for all of these vertex, all of the vertices. And it's going to be like the 2E, right, in undirected, and E in directed, right? In E, if the directed, because it's just one way. But if it's undirected, then it's going to be like two-way. Any question about this thing, guys? So this is the end of the class for today, right? This is only like this thing. We had the BFS. So I would like to say that like you're going to be responsible for entire thing in your exam, and please be prepared. And any question about the exam or the stuff that we covered in this lecture? If there's no question, guys, we can end up here. I will stop the recording.